In this video, we'll discuss section 7.5, which gives us a general strategy going over all different types of integration problems. So if you go to the first page in this section in your book, page 543, the first thing before we can talk about a general strategy is you need to know all your basic antiderivative formulas. Now, if you look on page 543, there is a whole big list of them right here. And the book has 20. A couple of them have stars next to them. But we've already simplified this a little bit. Certainly, you should know your power rule. You should know your 1 over u takes you to log of u, your e to the x, your basic trig functions. So, we've basically seen all these either in our very first list of what we knew coming into this class, or then we we expanded by adding about another 6 of those from chapter 6. So all the inverse tan, inverse sine. Again, if you just look at the table on page 543, 20 formulas, numbers 19 and 20 involve these weird, complicated logs. Definitely don't even expect you or want you to memorize those. I would expect you to use trig subs to get those results. But 17 and 18 give the inverse trig functions. 15 and 16 give a hyperbolic trig, which we're not going to use. We mentioned we'll leave numbers 12 and 14 out. We will ask about the integral of secant and tangent on their own, but we realize we could solve cosecant and cotangent in a similar way, but we'll simplify the list a little bit. Again, if we were meeting in person, that would be an absolute must to have that memorized. Here you get a little advantage online, at least enough familiarity to be able to use that chart. So now that we have that taken care of, what is our overall general strategy? And again, another point that we have to remind you about is that antiderivatives are not as friendly as derivatives. You come out of Calc 1, and especially once you get some new functions and their derivatives in Calc 2, and include the logarithmic differentiation strategy, there's basically nothing I could throw at you now, and you can't look at it and think about the different possibilities of, well, okay, in this situation, it's just a power rule or a product rule or a combination of chain product and quotient rule. We've got very concrete rules to follow, but you'll see as we go through this strategy, it's not a concrete list. It's, as we have always said, it's just a general list of suggestions, a little bit of a hierarchy, but in the end, it's all about making progress. So they start off with number 1 as simplify the integrand. I'd actually start off with number 1, is it already a known antiderivative? I would strongly say that should really be our first number 1. The basics are things attached by addition, subtraction, maybe just a couple of little rewrites, having an x in the denominator, bringing it up as a negative exponent. Those things should certainly be our first consideration. Is it a known anti? And if it's not, are there any simplifications, quick rewrites? I would kind of consider that number 1. But again, they kind of already expect that we've done that. So they're number 1. That's why, again, they start off with this idea of simplify if possible. If you go along with the book, they always give quick little examples, and you could certainly see those. I'll mention a couple of quick things. We've seen quick simplification. Again, those basic rewrites, trig functions, basic manipulations. 1 over cosine squared is secant squared. That's a good manipulation because it leads to a known antiderivative. So lots of things that we've been discussing since Calc 1. That's kind of where we'd start. If there's a problem of multiplication, this is what they show you in the book, by the way. They give you a quick situation where there's multiplication, so they multiply it. And then the second one, they start off with some trig, but they do a little bit of breakdown, and then they see a known trig identity that they apply. So again, this is not just a quick, always do this. This is a very broad category, but it's something we've been discussing for quite some time. Number 2, they talk about look for an obvious u sub. after you've exhausted the possibilities in step one. Okay, I can't simplify. There's multiplication that I can't multiply, or there's an inner-outer situation that I can't change, I can't manipulate in any way. Well, maybe number two, if you're stuck with one of those situations, look for an obvious U substitution. Well, again, what is obvious? That's not always quite so obvious to everybody. What one student sees, another student might find a little more difficult. But again, we've really been pointing a lot of these things out since the beginning. Go back to the beginning review video that we had and where we discussed antiderivatives. We talked about this. Obvious U subs, ideally we think about that. You see an inner function g of x and you see that derivative of that function or a close enough component that you could see a U sub would work. For instance, if I had an extra x squared and what I'm considering as my u has an x cubed, I should feel good because the derivative of x cubed would contain an x squared. It's not a perfect match, but it's close enough that we can make it work. So what are obvious u subs? Well, we talk about, again, u could be that inner function. We've seen other possibilities where we've just tried u as the denominator. That, once we start moving into something like this, now we're specifically aiming to get a 1 over u du. Or maybe we think of u as the exponent. But then again, we're hoping to end up with a e to the u du. Or maybe we're hoping to have one of the inverse trigs. So we're picking u to have a 1 over u squared plus 1. Or a radical 1 minus u squared. So things like that. Again, technically those are in the denominator, but just those are the things we've been looking for. Those are the possibilities. And then even outside of that, we've still seen more. So maybe now we're not getting to the obvious u subs, but trying a u to rationalize, right? We saw that at the end of 7.4. If you're having trouble with the square root of x, let's try u equal the square root of x, but then manipulate by letting u squared equal x and then take the derivative and substitute. So again, still, just every one of these steps, that's not just a one quick thing. There's a lot of things to consider, but again, establishing a little bit of a hierarchy, trying to do things as easy by hand. Is it a known anti? Can I clean things up and work with it on its own? If not, are there any good possibilities for u subs? And then if not, number 3, classify by form, by its form. And I would also note here, and by your experience. We've always said Calc 2 experience is going to make such a big difference. What have we done together that always is a good way to kind of think about, well, what can I do when I'm working on my own? So, classify by form. Now, again, if you're following with your book, they've got a lot of subheadings here, so I'll make a few notes here. So, classify by form, well, if they're all trig functions, thinking about stuff we saw in 7.2. What are the known trig identities? Are there any quick cleanups? Can we make that into a known trig antiderivative? If not, can we get one of those nice u sub situations? But that may involve some use of the Pythagorean identities, some manipulations to make that perfect. So again, one trig function to a power and the derivative of that trig function somewhere in that integral. So that's one possibility. In part B, we could talk about rational functions, polynomials over polynomials. That's what we saw in section 7.4. That's where we considered partial fractions. Okay? And again, it wasn't always just partial fractions. We saw a few other games we could play with those fractions. Sometimes those are the situations where letting u equal the denominator might work, but it all comes from this classification. And if we're looking at this and this u sub didn't work, and we're looking at a denominator we can factor, well, partial fractions is a good possibility to break that down, make it more simple. C, we'll talk about integration by parts. But that's already a technique. Remember, what did we say about integration by parts? Well, every once in a while you could be surprised by what might work out by integration by parts, but we consider two main categories: multiplication of simple functions, not functions with that inner-outer complication, just things like x squared times sine x, x cubed times log x, e to the x times sine x. Again, very, very basic functions, but there is a problem of multiplication, and there's no simple way to multiply them out. And the other one was one function, one simple function with known derivative and unknown anti. So we saw a few examples for natural log x, inverse tan x, inverse sine x. You know the derivatives of those, and that's all we're looking at, but you don't know the anti, and that's exactly what the integral is asking you to do. And now once you break into each of these, that gets you started with integration by parts, but then still the difficulty of just deciding, well, what should be u? Well, then what is left for dv? Does that work? Setting up the new integral, is it better? So again, all these things, that's just to get a good way to get started, but hopefully you've been getting plenty of good practice, and from that practice, once you establish what technique could work, that you're ready to go through, implement, and solve. It's always a problem in math class, everybody. It's one thing to know what it is, what needs to be done, but then it's a second thing to be able to actually go through and do it yourself. Okay, last one here. What other form do we want to consider? Well, again, the trouble with radicals. But even here, the two different considerations. The square root problems with all those known forms, the a squared minus x squared minus a squared, x squared plus a squared, those all led to the trig subs to clean up the radical, and then we were left with the trig integral after we were done. But then we also, again, we pointed this out at the end here, some of those other obvious u subs, well, again, not so obvious, but still trouble with radicals. If there's a square root of x or a cube root of x that's causing trouble, that might not be a bad choice to try for you. And now this is what should really make it clear that, again, all this is a general strategy. Step 4 is try again. If things aren't working, again, not everything is such a perfect fit. All integrals of this type go to this formula. All integrals of this type, there's overlap. There's places where problems could use different techniques. There's problems that are just not obvious. So again, try again. If the first 3 steps, this is from the book, if the first 3 steps have not produced the answer, remember there are basically only 2 methods of integration: substitution and parts. So try another substitution. Even if no substitution is obvious, just try something else. Try integration by parts. Again, that's a real funny one, but if nothing is working, at least integration by parts gives you something to manipulate. See here, they just talk about a general manipulation. I'm going to show you this problem in just a moment, so let me write it off on the side. And they've got a very similar one in the book to consider, but just something like that. That's not an obvious, and that's something that really can easily be stuck with right off the bat, but we'll come back and just see something that, I don't want to say randomly works, but just to understand, more experience gives you more possibilities of what can work. So manipulating the integrand. And when they talk about that, well, we mentioned lots of manipulation, maybe rationalizing, maybe a trig identity may be useful. So again, we'll come back and talk a little bit more about this specific problem, but still the idea of try again, relate to a previous problem. Again, if you've seen something similar before, try and apply that same technique to a new problem. And then last, try several methods. Sometimes we've seen it's not always just one technique. An integration by parts may eventually lead to a u sub. A u sub could lead to an integration by parts. A partial fraction may eventually still need a u sub or a manipulation. So again, it can't just have this idea that every one integral is just one technique. There is a lot of different overlap. So let's talk about a few examples. There are some good ones in the book. But if you start going in the homework and start going past problem number, I think it's 15. Yes, number 15. If you really start going past that, those problems can get really complicated in a hurry. And no matter how much you apply, it can really be quite a pain. So at the end of this video, I'm going to show you, I made an entire separate worksheet with something like 45 integrals on it so we can get some better mixed practice and not just have all those super hard ones, have some more middle of the road and even a couple of easy ones mixed in to make sure we're always sharp and we see all the different possibilities. But let's start with this one. So just looking at this, there's some division here. There's no easy, obvious cleanup. This is not a known antiderivative. So my first, just knowing the anti or simplifying, I'm not seeing anything. An obvious u sub, well, there's nothing obvious. There's no inner function. If you want to try u as the denominator, sure, u is 1 minus sine theta, du is negative cosine theta. There's no cosine to cancel with that. That u sub isn't going to work. If we think about classifying by form, well, it's only trig functions, but again, we kind of keep running around this. It's not a known antiderivative, and there's no obvious quick substitutions or manipulations to make. So now getting into the try again, manipulate. Let me just try, and let's try this. That's a legitimate move. And you should have seen things like this, whether it was in limits in Calc 1 or in other places. As long as I'm multiplying top and bottom by the same thing, it's a legitimate manipulation. It's like you're multiplying by 1. And let's just see what happens. Again, that's one of the biggest lessons here. It's not always going to be perfectly obvious what works. Even if you think you have a good technique, you still actually have to go through and do it. To see, it may seem like a perfectly good choice and sound strategy, but when you actually start to work, maybe things don't work out as you expected. Maybe there's an unexpected hiccup, and maybe there's a different strategy that may work better. So right now, again, I'm just trying. I multiply the top out, I get 1 plus sine. When I multiply out the bottom, I get 1 minus sine squared. Well, why did I choose to do that? Well, now you may realize I chose to do that. That's like the conjugate. We've seen that with radicals in Calc 1. Sometimes you saw that with manipulating limit problems. If you had something like the square root of x minus 3 in the denominator and you were getting in trouble, well, you'd multiply top and bottom by the square root of x plus 3, just trying to make some change. So that's similar, but the reason that change works is because now all of a sudden I've got an identity. That became an identity. Let me try making that manipulation. And even here, you still might think to yourself, well, did that really work? I've just made the situation worse. But I hope by now we've had enough practice that we realize fractions like this, sometimes they're ready to go just as is, but if they're not, that separation, separating them into two separate fractions might be the key. And now hopefully you're starting to see that we are getting on track. This one, now I'll treat them as two separate integrals. This one, 1 over cosine squared is secant squared, and that's a known trig antiderivative. Over here, some people might look at that and say, okay, now I'm ready with a trig integral. Now I'm in that good u substitution situation. One trig function raised to a power, and the derivative of that trig function also a part of the integral. If you let u be cosine, not cosine squared, but if you just let u equal cosine, this will work. You'll get an extra negative. That's not a problem though. You'll eventually end up getting this, an extra negative 1 over u squared du. Bring that up as a u to the negative 2, and you can take the anti using power rule. But others, that's one option, and maybe some of us see it that way, and that'll work. You'll end up getting plus u to the negative 1 here, and then when you back sub, plus cosine to the negative 1 power, plus c. But others might keep manipulating, and maybe you just play some games a little bit, break up the cosine squared and cosine times cosine. Well, sine over cosine is tangent, 1 over cosine is secant, and now no u sub, but now again we've manipulated to a known trig antiderivative, and we are done. So not obvious at all, but definitely something you could work with. But again, it needs practice. Now thinking about a couple of examples from the book, again, I've got a whole worksheet, so I'm not afraid to go through the examples in the book, and I'm not even going to solve them. All I'm going to do is just point out a few possibilities. Any questions, the book gives you the right track, and the book will continue to give you most of the rest of the answer. But even in the book, this is still mostly talking about strategy. So example 1, they start off with tangent cubed over cosine cubed. Again, a lot of problems. We've got division. We don't have any quick cleanup. It's not a known trig antiderivative. It is a trig integral. But with the trig integrals, what to do from here? Well, different possibilities. Some people might recognize that cosine in the denominator can be brought up as a secant in the numerator. Now, this is still not perfect, but we can still play the games with this. Maybe we say, well, if I want, I think I'm going to end up needing u as secant here, so I get a secant tangent as the derivative, which will leave a tan squared that has to be converted into secant squares. And then we'd have a good u sub. U is secant. So that's one possibility to work. Others, maybe we don't see that. We focus on the sines and the cosines. We do it that way. This is sine cubed over cosine cubed. Do a little work. You'll end up getting sine cubed over cosine to the 6th power. Still not perfect, but now this one is a little bit tougher just to realize you have to let u be cosine here, because that would allow you to have the one extra sine, and the other two sines can be converted to more cosines, more u's. So either way, both of these, some good manipulation, but no matter which way you do that first manipulation, there's still more trig work to consider, and ultimately you'd still end up with a u sub at the very end of this. If you look at the second example, so this was example 1, example 2, the integral of e to the square root of x dx. Again, I don't want to just jump to the final answer. I still want you to always be thinking from the beginning. This is not simple. This is not a known antiderivative. Thinking about u subs, we try u as the square root of x, but the derivative would be 1/2 x to the minus 1/2. There's no extra x's for that to cancel with. But maybe we're thinking about our experience. That u sub will still work, but it's going to require that little trick. So after you play with this a little bit, this would be manipulated into this through this u sub. And again, get your du, 2u du equals dx. That's how I finish this substitution. And we've traded one problem. We had a big problem here. Now we've got multiplication, but it's multiplication of simple functions. This is integration by parts. And this is very similar to the one I did the cosine of square root of x in the last video, in the end of 7.4. So that's a way to finish this one. Example 3 is a rational function, but here the degree of the numerator is higher than the denominator. You divide first, then you'd have your partial fractions. That's one we can definitely work through. Example 4, you've got a u as the inner function. So that one's not even bad. Example 4, let me write that one out. Example 3 is quite a bit. So just make sure you realize it's a rational function. Take a look at it. And again, they give you very little there. Make sure you go through, do your division. But that's, as far as strategy, really, really pointing us to partial fractions after we just clean it up a little bit. Example 4. Looks pretty messy right off the get-go, but this is one that after we've done so much hard stuff, don't overlook the easy stuff. That should be an obvious u sub. But again, I hate to use that word obvious. I almost wish the book did not use it because that makes people feel bad if they don't see something. What is obvious is, again, so much a matter of perspective. So I hope we've done enough so you do see that and be like, oh yeah, there's an inner-outer situation with the other mess. So that seems promising. And then once you take the derivative, look at that. There's the x that goes with that x in the denominator. Do a little manipulating, right? Multiply this x to here, and those will cancel. You'll eventually end up getting this. So still a little bit of power rule, bring that up as a negative exponent. And also that good reminder, just because you use the u sub and it works well, there's still some work for you to do. So that's pretty much it for this first part. Okay, I want to mention two other quick things just before we go. The book finishes a can we integrate all continuous functions? And we've already pointed out how easy it is to make up an integral that we can't solve with these traditional techniques. The book throws out 6 of them at the very end of the section, and we pointed out the integral of cosine x squared. They have put several others. So again, all of this is good strategy, but there's still more we have to discuss. I hope it's obvious. Anything I would give you on the test that comes from this chapter would be something that either from an earlier section or this chapter can be solved. But just to realize, unlike derivatives, where we have the tools to pretty much handle anything at this point, antiderivatives, we're still lacking, and we still have more we're going to learn later in this semester that'll answer these missing questions. Okay, the last thing I'm going to show you, and I'll email this to you so you have a full copy of it. This is my integral worksheet that I was talking about. So there are lots and lots of integrals here, and it is front and back. So that's what I mean. You've got lots of problems to go through. As I've said in the earlier videos, I think it's very important that you go through and do the homework in each section. And it's not a bad thing to kind of already have a little heads up that, yeah, questions from 7.1 are almost certainly going to need integration by parts. Questions from 7.3 are going to need trig substitutions. But it's good to be able to go through and get the practice in actually using those individual techniques. And now this is giving you the practice. Can you make that first good decision? How do I get started? And then can you go through and solve? So I would highly encourage you to take your time, even if you don't go through and solve all of these, to take some time, consider each one, think about what might work. My next video, I'm going to go through each one of these. I'm not going to solve them, but I'm just going to talk about strategy, what could work. And then afterwards, hopefully you go through any individual problems. Hopefully my strategy will get you on the right path. And then certainly any questions, you know the right strategy, but you still can't finish solving, we could certainly work on that as well. This is the last section for the test. We will quickly talk about 7.6 and 7.7, but this is the last section for the test.